All right, so now let's prove the Pythagorean theorem, but using similarity. So we're very familiar that Pythagorean theorem just states, one side squared plus one, or one leg squared plus one leg squared is equal to the hypotenuse squared, right? So we can prove it using similar triangles. So for example, in our triangle ABC, right? A is the right triangle, and so similarity can prove that AB squared, right, which is one leg, and AC squared, which is another leg, is going to equal our BC, which is our hypotenuse, right? So we're going to use similar triangles to justify this. So the first thing is, can we find all the different triangles? So go ahead and try to pause the video and rewrite these triangles as three separate triangles. All right, so if you're coming back, hopefully the first triangle you saw was our one that they originally stated. So this is our right angle. So this is our A, this is our B, and this is our C. Okay, I see a smaller triangle right here. So now A does not have a right angle. It's now D that is the right angle, and B, okay? But between these two triangles, right, they both have B in common. So I know that these two triangles are similar based on AA similarity. And then finally, my last triangle will be DC, where D is your right angle. So again, looking at these two triangles, I know it's AA similarity. And based on these two triangles, it's AA similarity. So all of these have at least one angle in common, or sorry, two angles in common. So that way we can kind of figure out what is happening, right? So again, it's all AA similarities, okay? So how can I use this now, okay? So Carol argues this great fact. She argues that the length of DB, right, over the length of AB is going to be equal to AB's length over CB. Okay, so again, I'm going to draw out all of the triangles and color coordinate them. So one triangle will be in blue. So C, A, D. One triangle will be in red. So A, B, D. And then one triangle will be in black. This will be our normal triangle, which was C, B, and A. Okay, so if these are all similar, which means all of the proportions should be the same. So when we look at our DB over AB, we're looking at our first triangle, right? So we're looking at our red triangle. So this is your DB over your AB. This is that first triangle. And the AB over CB, this is our larger triangle, right? AB over CB. So that way we can kind of see that we're checking out the ratio proportion here. And for the second part, the DC, that is your blue triangle, so DC over AC, and that is now equal to AC over BC. So that's our bigger triangle, AC over BC. So we can see kind of why this is happening. So do you agree? Yes, I agree with Carol. The reason why, because if your triangles are similar, okay, corresponding sides must have same ratio. Okay, so now let's let's get into her proof. All right, so we're not going to draw this one out in terms of a flowchart or a two-column proof. We'll kind of just answer her questions. So how can you use the proportions that Carol wrote to show that AB squared is equal to CD over BC? So basically all she did was this. She cross-multiplied. So she multiplied AB times AB, and then she multiplied DB by CB, right? So, and then she did the same thing here. She multiplied AC by AC and DC by DC. So this is part C. That's kind of what she did. So how can you use those proportions? If you want to get nitty gritty, right, we could say we could use our property multiplicative property of equality, right? So that's our true property that we use. Okay. So now let's think about this. AB squared plus AC squared is equal to CB times DB plus BC times DC. So basically, all she did was Carol just replaced, if I add these two values up, since AB was equal to this, right? This is what's equal to this, and this, or I should say this, is what's equal to this. All she did is kind of add things together. So part D, right, essentially kind of like if you did this, if you said like A was equal to B and C was equal to D, then if you added A plus C, that would be the same thing as saying B plus B, okay? The property known as the additive prop of equality, not that you have to remember that, but that's technically the property that we're using. Okay. All right. So let's jump to E. So why does this work? Okay. Well, if you think about it, the letters are switched. Okay. So if I do 2 times 3 is equal to 3 times 2, these are both going to give me 6, right? So I can kind of flip-flop these around and just say 3 times 2 is equal to 3 times 2. So that's exactly what we're doing here. We're kind of just flip-flopping those two together. So if we go to part E, right here, if I rewrite BC times DB plus BC times DC, what do they both have in common? They have DC, or sorry, they have BC. So we're factoring out that value, right? So we're just using, so we're kind of factoring out, this is technically the reflexive property, right? And we're using that to kind of figure out why that works. Okay, so let's jump to letter F. So letter F asks us a question. It asks us, what does DB plus DC equal to, right? Well, if I think about this, here is my DB and here is my DC. So if I add all of these up, I know that this is going to be equal to all of BC. So I'm going to write that. Let's say part F. So it said, what does DB plus DC equal to? That is going to be our BC. So basically, what they just asked us to do is how can I reuse that to write an equivalent expression? So here's our equivalent expression. So what I'm going to do is I'm going to replace BC with all of that, which means I'm going to say BC times BC, which gives us a BC squared. Okay? So, finish our proof. So why does this work out? All right, so let's go back. So part G, I believe. So why does AB squared plus AC squared equal to our BC squared? Okay, so what we're using is something known as the transitive property of equality. Okay, and all we're doing is kind of replacing things together. So we've already figured out what AB squared is and what AC squared is because we just added those together. So remember in one of our first parts, we added the AB plus the AC. And notice that AB and AC are our lengths, right? These are your legs. So these are your legs, okay? Or legs here, and then this is your hypotenuse, okay? And so I know that this is equal. So since these two values are equal and I've replaced this guy with part F step, right? That's the so basically you're just kind of replacing things together. Okay, so it's just known as the why does it work? It's known as the transitive property. And then again, this is just your Pythagorean theorem. So if you think about it, right angle, A, B, C, A squared plus B squared is equal to C squared. This is like your A, this is like your B, and this is like your C. So it's just a fun little proof to kind of help us with similarities. Okay, in part 3, what we're going to do is we're going to change a little bit. We're going to talk about distances, and so we're going to be looking at these 2 points, star A and star B, and we're going to try to figure out, we can always find the midpoint, that's easy, but what happens if we don't necessarily want the midpoint, right? So how we can find other specific lengths instead of just halfway distance between everything. So that's going to be our next video.